Hello, everyone. My name is Abdullah Ali. I'm a third-year PhD student at the University of Washington's Information School. Today, I'm presenting work on behalf of our collaborator, Dr. Meredith Ringel-Morris from Microsoft Research, and my advisor, Jake Wabrock, from the University of Washington's Information School. So the title of our talk is Crowdsourcing Similarity Judgments for Agreement Analysis and End-User Elicitation Studies. Before I get started on the work that we actually did, just in case not everybody here is familiar with what an elicitation study is, elicitation studies are a user-centered interaction design methodology, and they've been around in HCI literature for a while. In 2005, Wabrock et al. Published an elicitation study, and then in 2009, Wabrock, Morris, and Wilson published a CHI paper where they formalized the elicitation study methodology, and this paper in particular has been highly cited with over 90 published studies replicating the elicitation methodology, including one actually in this UIST coming up. That's really cool. So elicitation studies have been used to design natural interactions with for drone navigation, with TV system, smart TV systems, and designing interactions in augmented reality environments, just to name a few. The way they work is when researchers want to conduct an elicitation study, they invite a number of end-user participants, and they show them the effect of an interaction on a computing system known as a referent, and then ask them to propose the action that would cause that effect, which is known as a symbol. So throughout this talk, you'll see me talk a lot about referents and symbols. So just to reiterate, you see a referent, which is the effect, and then ask for the symbol, which is the action. After collecting a number of symbols for a referent, the researchers usually group those symbols based on their similarity, and then choose the symbol with the highest consensus to incorporate in the design of their system to trigger that referent. Because essentially you need to compare all of the symbols to each other in order to group them as groups, this takes a lot of time and effort, and this is the issue that we're trying to solve with this work. We decided to use a approach using online crowds and machine learning algorithms, and to do so, we set out to answer three research questions. The first one is, how can the crowd facilitate similarity judgments for agreement analysis in end-user elicitation studies? The second research question we wanted to answer is, how does the quality of the results produced by the crowd compare to those produced by expert researchers? And finally, by using the crowd, what are the benefits, if any, in terms of cost and time compared to the status quo use of expert judgment? So to answer our first research question is, how can we get the crowd to provide this agreement analysis? We created a web-based system called Crowdsensus, which is available for researchers, where they can upload a list of symbols, and then Crowdsensus generates a custom web pages that can be deployed to online workers, where they can vote on the similarity of those symbols. In order to design these interfaces, we did a number of pilots and tested different things like the prompt phrasing and ways to validate the votes that we're getting. And we also tested different ways to present different numbers of symbols together, which is what I'm going to expand on now. So we had three different designs of the interface. The first one was sort of a direct comparison approach, a one-to-one approach, where we showed two symbols next to each other and asked the crowd workers to vote either yes or no, whether they thought those two symbols are similar or not. The second interface we designed was sort of a list comparison, where we had one symbol at the top, and then below it there was a checklist of symbols, and the workers had to go in and check all the symbols they thought that was similar to the one at the top. Finally, the last one we had was a grouping interface, where all the symbols were presented as draggable elements, and the workers had to drag and drop symbols, creating groups. After a few rounds of testing, we ended up using the list comparison interface because it provided similar results to the one-on-one comparison, but it required less tasks, making it a lot cheaper to use. From piloting, people gave us feedback that the grouping one was just too confusing to understand. So how does this work? How do we get from a list of symbols to groups of similar symbols? So this is an example. The reference here is showing a list of cat videos, and the symbols that we collected from this hypothetical group of people are voice commands trying to get to that result. So the voice commands here are show me cat videos, I hate cats, personally I don't, show cat videos, my cool answer, and show me videos of cats. Using that input, on the right we see this screen generated by Crowdsensus. And suppose we give this interface that we generated to 20 online workers to vote on the similarity of these 5 symbols. The votes are stored in an agreement matrix in the Crowdsensus database, where the bottom matrix we see here is the number of people who voted, and the top matrix is the number of votes. To explain it further, for example, if we take symbols 2 and 4, we see that from the bottom, there were 20 people who voted, and on the top, 15 of those 20 people thought that symbols 2 and 4 were actually similar. And so then we take these pairwise similarity votes and turn them into a fully connected graph using an app that uses unsupervised clustering algorithms. And in this graph, we see the nodes are all symbols for one referent, and the edges between 2 nodes is how similar they are based on these votes that we have here. The app had 5 different clustering algorithms that we tested, which were hill climbing, shotgun hill climbing, simulated annealing, genetic algorithm, and coloration clustering. The task for these algorithms were to find subgraphs within this big graph where the agreement within a subgraph is maximized, but the agreement across different subgraphs is minimized. In the end, we end up with something that looks like this, where the similar symbols are all connected together, and in other words, we get a group of similar symbols. Of course, this is an example of only 5 symbols. In the real world, your result would look something like this, and this all connected red nodes are similar symbols where typically a researcher would have to do this manually to get this result. So back to our example, we got a group of similar symbols. Here, in other words, we got an analyzed result for an end-user elicitation study. So we see that show me cat videos is the right voice command to get results of cat videos online. Now that we were able to get the result that we needed, we move on to answer our second research question, which is how does the quality of the results produced by Crowd compare to those produced by expert researchers? To do that, we conducted an elicitation study based on Morse's Web on the Wall elicitation study, where we had 10 reference, which were web browser functions like close browser or go back or refresh and things like that, and recruited 43 participants from Amazon's Mechanical Turk to give us proposals of voice commands on how to do these functions, and ended up with a total of 430 symbols. Just as one does in an elicitation study, we did our own analysis and made groupings of similar symbols for each one of our 10 referents. And in addition to that, we recruited 6 experts, and they gave us each independently their groupings of each one of those 10 referents. Then we used Crowdsensus to get similarity judgments on similarity votes on these symbols from 410 crowd workers, and use the clustering algorithms to get groupings of similar symbols for each one of the 10 reference that we had. We compared the results that we got from Crowdsensus against the results we got from the experts, including ourselves, and we compared those on 3 different fronts, which were the agreement scores, the grouping similarity, and the symbol selection. In the interest of time, I'll only go into the process of this, the results of the symbol selection, and I would refer you to the paper if you're interested in full details about our results. In the middle here, we see the expert symbol, where we aggregated the symbols that all the experts agreed on to trigger one referent. And we saw that the expert's opinion converged for 8 out of the 10 reference that we had. And then looking at the Crowdsensus approach, we saw that there were the same symbols selected for all those 8. For the 2 reference where the experts' opinions diverged, and we saw that the Crowdsensus approach was able to actually resolve one of them. And finally, the last one just didn't have enough agreement among its symbols to select one symbol, either by the crowd or by the experts. Finally, to answer our third and last research question is, by using the crowd, what are the benefits, if any, in terms of cost and time compared to the status quo use of expert judgments? As far as cost goes, we saw that Crowdsensus was actually comparable to the experts, where per referent we paid experts $5. The Crowdsensus approach was almost about $6. The major benefit we saw was in time, where the experts took an average of over 3 minutes to analyze one referent. The Crowdsensus approach took about 0.78 minutes. In other words, Crowdsensus was 4 times faster than the expert approach, which is the status quo that's used right now. If you're interested in using Crowdsensus, you can head over to this link, where you can find information on how to access the tool and our paper, along with a list of essential papers you can read if you're interested in getting started with elicitation studies. I would like to thank the National Science Foundation, the Manny Charitable Foundation, Microsoft Research, and the University of Washington's Information School for their support of this work. Here's that link again and my email in case you wanted to reach out. Thank you all for listening, and I'm happy to take any questions.
Hi, Lydia Chilton, Columbia University. This is great. I'm really excited about it. One clarification, when you compared the crowd to the experts, were the experts using your UI or just their own?
No, their own. Like, we gave them an Excel sheet and we're like, go at it. Yeah.
So I'm wondering if you thought about, first of all, one issue is if the crowd does this for you and you're shipping a product, how confident are you in that? And is there a time when experts might actually want to do or be part of the crowd process?
Well, the crowd result can be sort of like a guideline for you, so you can tweak that result. So as a researcher, you'll have your own sort of notes and think alouds and things like that that you can consult in addition to the crowd. This is kind of lifting the burden of comparing one to the other and finally surfacing which one has the highest agreement.
I've got one as well. So I'm thinking about the argument that Corbin and Strauss make when they're talking about why you would use grounded theory, for example. And a lot of their motivation is that you as a thinker, as a researcher, gain insight into your own problem through the process of labeling and reflection and iteration. And I wonder if by sort of how much of that process, by making it extrinsic to the researcher, are you missing out on some of the important conceptual thinking that you'd be doing if you were going to be analyzing an elicitation study yourself?
Yeah, that's a really good question. I don't really know how much we'd lose, but again, you can look at the data analyzed rather than looking at the list kind of sporadically of seeing. So you'll gain, I think, better insight when you're looking at it as somebody else had already listed it in similarity for you. I guess you'll get a better understanding, maybe, or more context when looking at it that way. Yeah.
Hello, hi, Carsten Seid from Google. Thank you very much for the talk. I really enjoyed it. I've got a quick question regarding the user interface.
Yeah.
Do you happen to observe any relationship between, say, target position or group position in your UI towards attribution? So would you say, like, people, say, stuff that was positioned in the middle got more frequently attributed correctly, or position one was frequently skipped, anything like that?
We did not look at that, no. I don't think so.
Oh, okay. Thank you.
Thank you.
Hello, thanks for this wonderful talk. I have a quick question, is I can foresee when you're clustering things that there are items which may fall back into different clusters, and that the whole clustering thing is like a domino effect. You could have like two equivalent ways to separate things. So my question is, how do you deal with items which are ambiguous, which could be interpreted as different clusters?
You get more votes and see where they would fall, and that's kind of the job of the clustering algorithm, is to figure out which group should it belong to based on like if it's statistically significant or not.
All right, let's thank the speaker.
Thank you.